Yeah. Oh, an extra. Hey. All right. So again, the assignment, it would be great if I got it today because that way I can mark it and I can give it back to you for Monday. But if you want to hand it in on Monday, that's totally fine. I'm going to mark it Monday and hand it back to you on Tuesday. That's whatever, it's all good. Please recall that in Chemistry 20, a titration is a way of determining an unknown concentration of a substance. That's really the only reason why titrations exist. So a titration looks a lot like this. We've got some sort of an acid or a base. Now, keep in mind, titrations don't have to be acid-base reactions. Titrations can be precipitation reactions. Titrations can be, in our next unit, we're going to talk about redox reactions, the transfer of electrons, where acid-base is the transfer of a proton, right? So they don't have to be acid-base reactions, but often your experience is an acid-base reaction. So we got some sort of a base or an acid in our burette, right? Our titrant, and we've got some sort of a sample down here, which is either the acid or the base or whatever. So here is, in here, the titrant, and in here is either the sample or the analyte. Oh, that's not how you spell analyte. The analyte is the thing you're trying to analyze. So in here, for example, we've got a titration of 25 milliliters of 0.1 mole per liter hydrochloric acid with 0.10 mole per liter sodium hydroxide. Now I'm curious, in this example, the way it's worded right now, what is the sample and what is the titrant? Is the hydrochloric acid the titrant or the sample? The titration of 25 milliliters of this, if we're titrating something, this is the thing we're titrating, this is the thing we're titrating with, okay? So the titration of hydrochloric acid, in this case, this is hydrochloric acid, right? With our titrant. You always titrate a sample with a titrant. So this is sodium hydroxide. In our example, just the way it's written out there. Now, what do you do when you titrate something? Like, how do you titrate something? If you walked into a room and there was this set up and somebody said, titrate that thing, go. What would you do?
Open this.
Jaden.
You would slowly add titrant to your sample until you got a color change.
Yeah. You would slowly open up the valve here called the stopcock. So you'd open up the stopcock and then liquid would hopefully slowly start pouring down. And then eventually you would get a color change. Now in reality, what we usually do on the first trial of a titration, we open it up full blast and we let that thing rip. We just let it go. And we let it go until we know approximately how much titrant was needed. Did you ever do that in Chem 20?
Yes.
Your first trial, you always you let it open and you just let it rip and you just cruise through that first trial. Because there's no point sitting there waiting drop for drop for drop for 35 minutes, right? That's a waste of your time. So you just let that first rip, sacrifice the first trial, and then you know approximately how much volume to use the next time. So, okay, all right, whatever. This is the titration curve of a strong acid with a strong base. So if it's a titration of a strong acid with a strong base, what are we starting with here? Using that title, what are we starting with?
Strong acid.
We're starting with strong acid, right? So what's our pH going to look like initially? Is it going to be high or low?
Low.
It's going to be low because we're starting with an acid. So it's going to be like this. Does the pH have to be 1 to start off with?
No.
No, it could be 5 to start off with. You can have a strong acid if it's really dilute. You can have a strong acid with a pH of 5. It's whatever. So it's the pH doesn't tell you if something's a strong acid or a weak acid. It's how concentrated is it. Now, what's going to happen? What are we always constantly adding? What are we literally never going to run out of in this? A base. We're never running out of a base here. We're always adding a base. So what's going to happen to my pH? It's going to rise, but in a very characteristic fashion, okay? It's going to slowly go up, and then it's going to shoot up, and then it's slowly going to flatten out. That's the way we get a pH curve. It's going to rise slowly, 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 slowly. And then for those of you who are like really mathematical, because pH is a logarithmic value, changes that are at the extremes are very small, but changes in the middle are very dramatic. So this is the reason why this curve has this look, is because pH is a logarithmic scale. That's the only reason why. So it's going to change slowly, and then it's going to change slowly again. And then eventually, it's going to flatten out, because now we're just diluting the base. We're just adding more base, more base, more base. So what would be the Bronsted-Lowry reaction or equation for this particular reaction? Let's figure out our major entities in solution. What are our major entities here for these two things?
Hydrogen, chloride, and
We've got hydrochloric acid and we've got sodium hydroxide. So what's the first major entity somebody wants to spring on me? Sky?
Chlorine negative.
Do we have chloride ions in here?
Yes.
Yeah, we do. Of course we do. Absolutely. What else do we have? Yeah. We have hydronium. Why do we have hydronium? Why didn't somebody say hydrochloric acid? It's a strong acid. It literally doesn't exist in water. Now it does, right? 0.00001% does, but whatever. So we've got hydronium. What else are we going to have in our solution? That was the HCl. So we're done with the HCl. What else do we have? We do not have NaOH. We do not have NaOH. We do not, do you want me to repeat that a couple more times? We do not have NaOH in our solution. Do you understand? We do not have NaOH. I know it says it right there. I get that. Why do we not have NaOH? It's ionic, and it's split up. We don't have NaOH, but what do we have? We've got sodium ions and hydroxide ions. Because it's ionic and they split up, we've got those. Okay, all right, and we also have water. So what's the strongest acid and what's the strongest base here? Jaden. Yeah, we've got our strongest acid and our strongest base. So the Bronsted-Lowry reaction, we will react the strongest acid with the strongest base. H3O plus reacts with hydroxide. And this is about as quantitative as a reaction as you'll get. So you'll get what? If the acid transfers a proton to the base, what's hydronium gonna turn into? Water. And what's hydroxide gonna turn into? Water. Water. Good. All right. So tell me, what I want to know At equivalence, if this is totally theoretical, okay? If we added the exact same quantity of this as this, so no more of each other, right? 50 of these and 50 of these. They turn into 50 of those and 50 of those. What would be the pH at equivalence?
7.
Yeah, 7. We would get a pH of 7 at equivalence. And what do you notice about the very, very carefully drawn graph? I'm a crap artist, but I'm really good at drawing pH curves. What do you notice about the equivalence here? It should be at 7, and I think I spoke too soon. I kind of went up. I kind of had to fudge that line a little bit, but you know what I'm talking about. The pH at equivalence for this particular reaction will be 7. So when you have a strong acid and a strong base, that's a strong acid and a strong base will always make water when it reacts together. It will always have a neutral equivalence point. So what's going to be the indicator you would like to use for this endpoint? Do you remember this from Chem 20 at all? Kind of?
Oh, it's
Yeah, it's in your data book. You don't have to memorize it, that's for sure.
7.
Look at your data booklet. It's a pH of 7, yeah? Oh, so good. There's 2 of them. You can use 2 of them. Okay? Now, remember, the indicator should always change color during equivalence, or that's what we call the endpoint. So we want the pH range change. We want the color change to fall. We want the equivalence point to fall in there. So the first one, 0 to 1.6. No, 7 is not in between those 2 things. Is 7 in between those? No. What about Cresol red? Would Cresol red be okay?
Yes.
No. That's too far. It's at the extreme end. It's at the extreme end of this color change. I would never use Cresol red for this. Okay? Are we okay with that? All right. Keep going. No, 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 no. Ooh. Ooh. So bromophenol blue, is that okay?
Yes.
Yes. And is phenol red okay?
Yes.
Yes. Okay, it's not at the extremes. It's not outside of it. Good. Awesome. So we could either use bromothiamol blue or phenol red. That's my doctor writing. That's a Chem 20 thing. Okay, let me know if you have any questions about that. That is just review there, okay? You may be asked about that on the diploma exam or something like that. Okay, let's scooch. Now the equivalence point versus the end point. Let's go back. I'm going to go back. You don't have to go back. I'm going to go back. I'm going to go back. You don't have to go back. When I go back here, the equivalence point, what is the first half of the word equivalence? Equal. Equal amounts. Not equal volumes, not equal concentrations, equal amounts. Okay? If I added, in my titrant, in my sample, if I had 50 million ions of hydronium, how many ions of hydroxide would I need to add in order to get equivalence? 50 million. Do you know what I mean? That's what equivalence means. Now, the equivalence point is a totally theoretical point. It is impossible to reach equivalence in a titration. Because think about it this way. If I need 50 million of those ions to match those ions, right? Every drop contains 190,562. Is it possible to get exactly 50 million from 190,562? No. Do you kind of see what I'm saying? It is impossible to reach equivalence. But in between two drops, there's a theoretical point that we did reach equivalence, okay? We call that the endpoint because hopefully the color will change. Equivalence, this is the equivalence point. This is a theoretical point where we've got equal amounts of titrant and analyte, okay? What you see physically in the lab is the endpoint. So we often use an indicator to indicate when the equivalence point happens. But you can't stop on an equivalence point. You can stop at an endpoint because you see the change in indicator. So we use an indicator to identify approximately when the equivalence point happens by using a change in color. We call this change the endpoint, okay? What would be an appropriate indicators for the two endpoints here? Do you know where the two endpoints are here? The endpoints are always in the middle of the steepest parts of the curve. In the middle of the steepest parts. So I see a steep part here. I'm going to look for the middle of it. So what I like to do is I like to extend that line and extend that line and go halfway in between. What pH is that? It's just below 5, maybe, just barely below 5. So let's look for an indicator that will change just barely below 5. Okay, let's see. Would chlorophenol red work? No, because barely below 5 is too low, right? Would methyl red work? Pretty tight. I said barely below 5, so 4.9. 4.9 is in this range. So yeah, it's not wrong. I'm just saying if you were to be a chemist and you wanted an appropriate indicator, probably that's a little bit too far. Okay, but whatever, that's fine. So I will accept methyl red, that's fine. But bromo-cresol green, can you see how, like, just barely below 5, i.e. 4.8, 4.9? 4.8, 4.9 is right smack dab in the middle, basically. So bromo-cresol green, I would be happy with. Methyl red, I would totally accept. It would not be wrong. I want to be very clear. But just in the lab, if you were to choose an indicator, there's one would be better than the other. So here, I would say bromo-cresol green. And as the last thing you do today, figure out the second indicator.
Please go to the bookstore. There's popcorn on sale across from the office. And it is your last chance to order CTS ware and Hot Rod Club hoodies. Please see Mr. Wade if you are wanting to order those by today. Thanks.
The next one is like 9 point something, 9.5 maybe, pretty close to 10. So phenolphthalein or thymolphthalein would work, right? Phenolphthalein or thymolphthalein would be fine. Cool. The assignment is due on Monday. Your major assignment is due on Tuesday.